Hey guys, what's up? Welcome to the GPA Factory ECO329 Exam 1 review, coming to you live from my padded cell. Yeah, I know, it looks awful. You can kind of see where the outline is. There it is, whatever. We're going to be covering everything you need to know for ECO329 Exam 1. That's going to be a lot of probability, Bayes rule, Venn diagram probability, tree diagram, also calculating a bunch of means, standard deviation, median, first quartile, interquartile range, linear transformations, all of that good stuff. It's going to be covered in this review. It's probably going to be separated into two parts because you probably can't rip through 2 hours of economic statistics all in one go. So feel free to break it up into two pieces. We're going to cover all that. Plus, there's a mock exam at the back of this packet. Plus, I get to tell you about who I am in case you don't know who I am. That's fine. I don't know why I sound so pretentious or narcissistic about that in case you don't know who I am. But all right, we're going to just have a look at a bunch of math that you were like, I hate math. That's why you guys are coming here. So let's go ahead and have a look. Oh, there's our good looking logo. This is, like I said, the ECO329 Exam 1 review. So if you're not in that class, I don't know what you're doing watching this video. All right. I would talk more about myself, but I'm going to skip that page. I will just say a little bit about me. Number one is I've been doing this stuff for probably longer than I care to admit. 15 years of math tutoring, stat tutoring, econ tutoring. Any sort of math question that you have for me, I can probably answer it because it would excite me because I love math. That's why I don't get invited to parties. But yeah, I love helping students. I want to make sure you guys walk out of here thinking, oh my God, I can actually crush this exam. So I'm going to cover all the topics from front to back and make sure you know it all. So we're going to start with some sample space and let's get to it. So my trusty green marker, black marker, where's my blue marker? Bam. Hope you guys are ready. If you have any questions, let's talk about this real quick. If you have any questions, you can always email me at andy@gpafactory.com. Hit me up. If something confused you, happy to help. If you want to meet somewhere and talk about like statistics and like, hey, I need to practice some hard problems, hit me up. I'm happy to help. I want to help. In all seriousness, I know I've kind of been goofing around for these first 5 minutes, but I do want to help and make sure you guys get as good a grade as possible. Yeah, we're going to rip through everything you know in 2 hours. So here we go, starting now. Sample space. Sample space is a set of all possible outcomes for a random event. There are two simple examples. Heads or tails, right? Like when you flip a coin, either comes up heads or comes up tails. Those are all the possibilities. Other simple examples when you roll a die. 1, 2, 3, 4, 5, 6. That's it. Those are all the possible cases. Some other additional terminology, disjoints if they have no common elements, also known as mutually exclusive. So you might see this phrase thrown around as well, but disjoint and mutually exclusive mean the same thing. Two events are collectively exhaustive if their combined events make the sample space. We'll see more of that in a second. Let's start with question 1. The University of Texas Longhorns have 2 remaining drives in the waning minutes against the Mississippi State Bulldogs. Don't worry, Texas is already crushingly ahead, as we know they should be. Each drive can end in 0 points, 3 points, or 7 points. We want to know what's the sample space of the number of points in these next 2 drives. Remember, there's 2 drives, okay? And you can get 0, 3, or 7 points. So what's possible in 2 drives? Well, unlikely, but it is possible that UT scores 0 points in both drives. So 0 plus 0, that makes for 0. Okay, well, what else could happen? This is where your job is to like try and think of all the possible cases that could happen on these 2 drives. So we just dealt with one. The unlikely case that Texas scores 0 points on 2 drives. But what about maybe they score a field goal on one drive, but no points on the other drive? Okay, that would be 3 points. What else is possible? Touchdown, and then no field goal or no score on the other drive. So 0, 3, 7. What else is possible? 2 field goals. So field goal on the first drive, field goal on the second drive. Okay. What else is possible? I think you can get a field goal on the first drive and a touchdown on the second, or vice versa. Touchdown on the first, field goal on the second. That would make for 10 points because you got 7 plus 3. Or finally, 2 touchdowns. Obviously, the optimal outcome, 2 touchdowns makes for 14 points. And I think that enumerates all the possible cases that you would get with 2 possible drives. Yeah. Cool. I think that's everything. All right. Let's do another example. Andy and Grant play a series of chess games. They stop playing when one of them wins 2 games in a row, or until they complete 5 games. What is the sample space of this experiment? Let's start with the simplest case. Let's just say that I'm a genius. We'll say A means I won a game. So AA means I won 2 games in a row. The series is over. It also could be the case that Grant wins 2 games in a row. So let's say he wins the first game and wins the second game. There it is. That game's over. Now what else is possible? Let's imagine the series goes to 3 games. Well, in that case, I won the first one, but then Grant won the next two, or vice versa. Grant won the first one, and then I won the next two. So those are your 3-game series. And again, remember, the series terminates when someone wins 2 in a row. All right, let's go on to 4 games. What else is possible? Well, a G, remember, that would have to start out this next sequence of 4 games because you can't have someone winning twice in a row. It could not do another G because I've already got that guy and the series would terminate. So it has to go back to me. So I win, then Grant wins, then I win. And let's say I win 2 in a row starting there. So I've got me, Grant, me. That terminates the sequence because there was 2 in a row. But of course, I could flip everything. It could be the case that Grant wins the first game, then I win the second game, and then Grant wins the next 2. And then we've got our last 4 possible cases. It's I win, Grant wins, I win, and then Grant wins twice. Or Grant wins, I win, Grant wins, I win twice. Or maybe we just traded games the entire way through. Grant, Andy, Grant, Andy, Grant, Andy, all the way through. So that would be G-A-G-A-G or A-G-A-G-A. Now you might say, well, wait a second, why did these get included? Well, you got to remember, the series or the experiment stops if we complete 5 games. So there is no 6-game series. There's no possibility where there are 6 games are completed. So this would terminate the experiment because we played 5 games. We swapped games back and forth, G-A-G-A-G or A-G-A-G-A. That makes the full sample space. I want you to take note of what I'm doing here. I'm just thinking, well, what's possible? It could be the case that I won 2 in a row at the very start. Or it's possible that I won the first, but then Grant won the next 2. So I'm enumerating all the different possible cases. There are ways to do this that are more clever than the way I was doing that, but for now, I just want you to be able to recognize the possibilities when going through all the possible cases of a certain experiment. Let's talk about A be the event that Grant wins a majority of the games. All that means is I want you to create a set called A, and from the sample space above, we'll call the sample space S. From the sample space above, write down all the ones where Grant won the majority of the games. So sample space A would be GG, AGG, GAGG. Grant wins the majority of the games here, so AGAGG. And lastly, we've got GAGAG. GAGAG. Okay, these are all cases where Grant won the majority of the games. And then B says, be the event that an odd number of games are played. So an odd number of games would be the 3-game series, AGG and GAA, as well as the 5-game series that are here. I don't even know if I want to write all these, but I'm going to because I'm a sucker. GAGAA, GAGAG, and lastly, AGAGA. Okay. So that's event A, that's event B. First question says, are A and B disjoint? So the question is, do these guys overlap? Is there any overlapping value in both of these? Yeah, I see that both A and B have AGG. Now they probably have more. I think they might also have GAGAG. That's fine. But so long as there is one common element, they are not disjoint. Not disjoint, aka they're not mutually exclusive. Okay, are they collectively exhaustive? That is to say, if I were to put all these together in one set, would they be the sample space? And I think the answer is no, because have a look. I think we're missing AA. This guy here, AA, is not listed anywhere in these 2 sets. So it's not collectively exhaustive either. So not collectively exhaustive. Remember, collectively exhaustive means that if we were to put all these in a bucket together, we would get the entire sample space. And since it doesn't seem as though we would get all the values, I don't think we're getting AA here, then it seems as though it's not collectively exhaustive. Okay, we are done with sample space. Let's move on to counting, some basic rules of counting. The word and usually suggests multiplication or suggests addition. The phrase without replacement means you're not putting the drawn object back in the bag or bucket or wherever you're drawing it from. And then with replace, it means the drawn object goes back into the pool or the bucket or the bag. Let's do an example. Cooper is setting up his schedule for next semester and must choose one of each of the following classes: finance, economics, foreign language, and an elective. If there are 3 finance classes, 4 econ classes, 4 foreign language classes, and 5 electives, how many class schedules can he make? This is an and situation because he has to choose a finance and an economics and a foreign language and an elective. So because I have 3 finance classes, I have 4 econ classes, I have 4 foreign language classes and 5 electives. These are all the possible different schedules that can be made. 3 times 4 is 12, times 5 is 60. I think this is 240. 12 times 20, yeah, 240. Cool. That's it. All I did was multiply. The reason I did that is because the word and tells me that I should. So I'm multiplying because of that word and. I said I have to get a foreign language class and an economics class and a finance class and an elective. I'm going to juxtapose this with my or example. This is an or example. My really weird high school psychology teacher had this seating chart look like this. And each student was assigned one of the alphanumeric combinations that you see to the right. So I was maybe D2 or someone was C5. The question wants to know how many students in this seating chart have an even number or a vowel. So let's start with the even number. Okay, so it looks as though we've got 5 of them here. There's 5 even numbers, all the 2s, and then there's 5 of 4s, which are also even numbers, just in case you didn't know. So we've got 2 and 4. We've got 10 of the even numbers. We've got 10 even numbers. Or it could be a vowel. Now notice you'll notice I'm doing a plus sign. Why am I doing a plus sign? Because I said even number or a vowel. So what else is possible? The vowels, in case you don't know, vowels are A, E, I, O, and U, and sometimes Y. In this case, the only vowels I see are A and E. So it looks like we've got 5 instances of A and 5 instances of E. So 5 and 5. B, C, and D are not vowels. They're considered consonants. So A and E are the vowels. There's 10 of those. Now you gotta be a little careful because you'll notice, some of you, the astute among you, will notice that I've counted these guys twice, right? These guys were guys that were both vowels and even numbers. So I gotta make sure I don't double count them. I'm gonna subtract them out. I don't wanna count these twice. So there are 16 possible different combinations. And here they are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 12, 13, 14, 15, 16. There they are. Those are all 16 cases where either a vowel or an even number. Notice I'm adding to get those rather than multiplying. All right, last question here on this page. Chris is deciding what he wants for lunch, which consists of an entree and a drink. If he goes to Pluckers, he can choose from 5 entrees and 3 drinks. If he goes to Torchy's, he can choose from 7 entrees and 2 drinks. If he goes to In-N-Out, he can choose from 3 entrees and 3 drinks. Now, if he only goes to one restaurant, how many different combinations can he have for lunch? So here's the deal. He can go to Pluckers, or he can go to Torchy's, or he can go to In-N-Out. And because I'm saying or there, I'm going to kind of do each scenario. I'll do Pluckers, or Torchy's, or In-N-Out. Okay, let's start with the Pluckers case. 5 entrees and 3 drinks. So how many combos can he make? 5 times 3 will be the number of combos he can make here. 5 times 3. What about Torchy's? Torchy's is 7 times 2. 7 entrees, 2 drinks. And then lastly, In-N-Out has 3 entrees, 3 drinks. So that's 3 times 3. 15 plus 14 is 29, plus 9 is 38. So there's 38 different possible combinations for lunch. Should almost last him, once, I don't know, a few weeks, depending if he goes every day. Okay, that does it for some basic rules. And again, I want to point out that this one used both rules. Again, the highlight here is that there was the drink and an entree. So I had to multiply because I'm saying entree and drink. But there's also the or case because I could eat at Pluckers, or Chris could eat at Pluckers or Torchy's or In-N-Out. And so that's where the addition comes in. So you notice that and and or are usually cluing you into how you should add or multiply some of these values. All right, probability. I'm just going to talk about some notation on here, and I'll set up some Venn diagrams. I don't know how much set theory is going to be on your exam. Like, I'm not expecting you to have to draw anything on your exam, but it helps get a sense of what these variables, this notation means. So P of A is the probability that event A occurs. P of B is the probability that B occurs. With this little superscript C, what that means is the complement occurs. So that means not A. So everything outside the A bubble. You might also see some similar notation, A bar or A prime. A intersect B, this is intersect. So this upside down U means intersect, and I will sometimes say that word, intersect. But it also means and. Whereas this U is union, and it means or. Okay, so let's highlight those words. I want everyone to highlight where I've said and, my and, here's my or. Okay, let's sketch the events by shading the appropriate regions below. So P of A is shading the entire A bubble. There's P of A. Just shade that bubble. Don't be perfect. Don't feel the need to add the entire fill the entire thing. A complement. So this is probably a complement. This is everything outside of the A bubble. So that would be everything outside of A. Again, I'm not going to try and get everything, but everything outside of A, and that's what that looks like. Okay. A intersect B. That's just this overlap. Just the overlap. That's A and B. A or B is everything inside both circles. That's A or B. And now let's try some practice problems. Sketch the event A complement intersect B. So this says I want to be outside A and inside B. So where would that region be? I want to be outside of A, but inside of B. That would be this region here. This would put me outside of A and inside of B. So that's what this region looks like. What about sketching the event A union B complement? So I want it to be inside A or outside of B. This is an or. So inside of A or outside of B. When it's an or, you're actually going to be shading a lot. So inside of A, anything get inside A works. That works. But also anything outside of B. So that would be all this. Anything outside of B also gets shaded. So it looks like everything but this little crescent sliver here on the right. So this is what P of A union B looks like. Again, I don't expect you to have to shade anything on your exam. It's doubtful that you're going to be doing any sort of shading, but I just wanted you to get a sense of where these regions are. If ever like, what's the probability of A intersect, B complement or whatever? Could you be able to do that? Could you be able to figure out where on your Venn diagram that would occur? Okay, let's do some really easy probability rules. This is where I've mentioned disjoint again, but again, disjoint means mutually exclusive. So I just want to remind you, mutually exclusive is a synonym for disjoint. Got some other rules here. This is the addition rule. So A or B is A plus B minus A intersect B. This is the conditional probability. We'll get there in a second. We're not going to use 3, not too much just yet. And then independent, again, we'll get there as well. We're not going to use these rules too much, but I'll kind of invoke them as we need to. So let's start with problem 1, or on probability rules. Suppose that 20% of UT students are going to ACL weekend 1, while 15% of UT students are going to ACL weekend 2. Additionally, 3% of students are going to both weekends of ACL. So I'm going to do this. I'm going to say, draw some circles. I think the Venn diagram is so super helpful here for this situation. And I'm going to say weekend 1, I'll just say WK1 for weekend 1, and then WK2 for weekend 2. Okay. Now we are told that 20% of students are going to ACL in weekend 1. Now it might be tempting to put 0.2 here. Everyone's very tempted to see when they see 20%, they want to put a 0.2 here. Don't do that, because we don't know how this 20% gets broken up between this piece and this piece. This whole bubble is supposed to be 20%. So maybe this is 10 and this is 10, or maybe this is 15 and this is 5. We don't know how these two numbers are supposed to add up to 20. So don't put all 20 here. And for the same reason, we can't put 15% in this bubble. A lot of people, again, are tempted to put a 15% here, but again, I don't know if this 15% is split up to be, 5 here and 10 here, or 3 here and 12 here. I don't know that 15% gets divvied up. But however, I am told the last value, namely that 3% are going to both. That is to say, the probability of weekend 1 and weekend 2 is 0.03. The overlap section, the middle piece, is 0.03. So I'm going to put 0.03 here in the middle. And now that I know 0.03 is the overlap value, I can then figure out how much goes into weekend 1 on the left and weekend 2 on the right. So remember, weekend 1 was 20%. 3% of it has already been used up, so there remains 17%. Similarly, 15% was all of weekend 2, but again, 3% has been used up, so that leaves behind 12%. You might notice that these probabilities don't add up to 100, and that's an issue because they're supposed to, right? Probability all to add up to 1. Well, that's because there's one last case. So the people who don't go to ACL, right? These are people who go to ACL weekend 1, but not weekend 2. These people on the right go to weekend 2, but not weekend 1. And these people in the middle go to both. Well, there's a fourth group of people, and those are people who don't go to ACL at all. So what remains? Well, 17 and 3 is 20, plus 12 is 32. So what remaining percentage is there? 1 minus 0.32 is 68%. So that's going to go out here. And now that we've got our Venn diagram, we can answer every question that ever gets thrown at us, okay? First question says, what's the probability that a randomly selected student is going to at least one weekend of ACL? At least one weekend, at least one here, means one, the other, or both. When we're talking about Venn diagrams and I see at least one, I want one bubble, the other bubble, or both. So which of the regions in this Venn diagram count as one, the other, or both? Well, 17% is in this one, so that counts. 0.03 is in both, but that's fine. Weekend 2, 0.12 is in this bubble, so we count that. The only one we don't count is the 0.68. So we're going to add up all the values here, and I get the probability of at least one. We'll just say P of at least one is equal to this plus this plus this, which we've established already is 0.32. Okay, let's do another. What's the probability that a randomly selected student won't go to either ACL weekend? Well, now I just look at my chart. Which one of these is neither weekend? The 0.68. So probability of neither weekend is 0.68. All right, one more question. What's the probability that a randomly selected student won't go to exactly one of the ACL weekends? This is tricky. Won't go to exactly one. So remember, you can go to 0 weekends, you can go to none, you can go to 1 weekend or the other, or you can go to both. So 2 weekends. That's all that's possible up here. But we want the cases where you won't go to exactly one. So 0 or 2 are the cases that we want. 0 weekends is 0.68. So let's write that one down, 0.68. And then 2 weekends is 0.03. So we're going to add that one on top of the 0.68 for an answer of 0.71. These are the people that don't go to exactly one. They go to either 2 or they go to none. So that's a tricky wording. Won't go to exactly one is the wording there. Make sure you're paying close attention to the wording here, because all the wording is going to tell you is which part of your bubble you should be in. Okay, let's do some more. This is going to be counting. So I didn't really title this page, but this is going to be some practice with counting. Okay. According to the Texas Department of Motor Vehicles, each standard license plate consists of 3 letters followed by 3 digits. The letters cannot be repeated, but the digits can. How many different license plates can be created? Well, I like to do this when I'm given a license plate problem like this. I just draw blanks and I write down the number of values that are possible to go in these blanks. So for instance, I have 3 letters followed by 3 digits. Well, there are 26 letters, so I have 26 choices for the first placeholder. Can letters be repeated? Well, it says the letters cannot be repeated. The letters cannot be repeated. So whatever letter I chose here, I can't choose it again. So I have one less choice for the future. Let's say times 25. And in a similar fashion, well, guess what? I couldn't choose if I already chose. I chose a letter here and a letter here. I can't choose from those 2 letters, and so there's 24 possibilities going forward. And now we're going to talk about the digits. Well, there are 10 digits, 0 through 9. 0 through 9 is 10 digits, and these can be repeated. So when I'm picking my digits, I can do 10 times 10 times 10. The reason I can use 10 all the way down is because I could repeat the same digits. So I could get 777 for all those digits if I wanted to. And so this is your answer. Let's grab a calculator and play the multiplication game. 26 times 25 times 24 times 1,000, because that's what 10 times 10 times 10 is. 15 million, say 15600,000. Fantastic. What's the probability that a license plate created this way doesn't contain a Q or a 7? So it doesn't contain a Q or a 7. Well, I'll draw my blanks. I cannot pick a Q, which means my first letter can be anything it wants to except Q. So I'll put 25. Then I say, well, my next letter, again, I can't repeat letters, so my next letter can't be the first one that I picked or a Q. So now I have 24 to choose from, and similarly, I will have 23 letters to choose from as I get there. I also cannot contain a 7, so I only have 9 digits to choose from. I normally have 10, but because I can't choose a 7, I have to choose 9 digits here. And so this tells me the number of different possible probabilities or possible license plate I can make in this way. So this is 25 times 24 times 23 times 9 times 9 times 9. So about 10 million, 10 million, 60,200. Okay. Now I want a probability. So these are all the ways that you can create a license plate without a Q or a 7. But I need to divide that by the total numbers. So 100, 60, 200 divided by 156,000,000, and that comes out to be, let's go find out, this value divided by, let's say divide this by the previous, so just divide by 156,000,000, 0.6449. That would be what we have there. Okay. Next question we have, what is the probability that a license plate created this way consists of 3 consecutive letters in order? So that is to say something like A, B, C, or D, E, F, or M, N, O. This is tricky. So 3 consecutive, how can that happen? It's always good to think about how is this possible? How could it be possible that you get 3 consecutive letters? Well, let's say the first, you might think, okay, my first choice can be anything, but then the next letter must be the subsequent letter. Like if I picked an A, then the next letter has to be a B. Then I don't have a choice here, right? And once I have the B, I have to pick a C. I can't vary in my choice after I've selected the first letter. Some of you will notice a problem with this though, is that what if I start my license plate off with a Y? Well, then what are the next consecutive letters? You could do Z, but then what comes after Z in the alphabet? Well, nothing. So I couldn't do a Y. And similarly, I couldn't start my license plate with a Z because, again, what's the next letter? There is no next letter after Z. So I can't pick any letter to start. I can only pick one of 24 letters. So this isn't quite right. I can only pick one of 24 letters. A all the way to X. I could pick X because if I pick X, then I could get Y, and then I could get Z, and I'm happy. But these two, I can't make a license plate that starts with a Y or a Z where the letters have to be consecutive. So again, I could start my license plate with either A all the way down to X, but then the next 2 letters have to be whatever follow them in the alphabet. So these guys are locked in. And then I have to do, don't forget, I have to do the numbers. Now, there was no restriction on the digits. It doesn't seem as though I can't say, oh, you can't have a 7 again, or you can't have any odd numbers. No, it just says play however you want to with the numbers. So I have 10 digits times 10 digits times 10 digits because those can be repeated. So my answer there is 24,000. There's only 24,000 license plates that go ABC followed by 3 numbers, or MNO followed by 3 numbers, or XYZ followed by 3 numbers. Cool. And then this is a tricky question. The professor has done something like this before. What's the probability that a license plate created in this way consists of 3 of the same letter and 3 of the same digit? Well, you have to remember, letters can't be repeated. So 3 of the same letter is not possible. He has done this before. Probability is 0. This is a trick question. It's not possible to get 3 of the same letters, again, because, as a reminder, letters cannot be repeated. So you can't get 3 of the same letter. So there is no license plate that consists of 3 of the same letter. You cannot get GGG742 because you're not allowed to have letters repeated. So that's why the probability of getting a license plate number or a license plate like this is 0. All right, we're done with counting. Moving on to independence. Independence refers to the property that the outcome of one event does not influence the other. So for example, if you know the outcome of the one coin flipped, it doesn't change the outcome of the next coin flip. But on the other hand, if you know that someone's taking an accounting class, you might be more inclined to believe that they're probably in the business school. So those events are not independent. The rule you're going to use for independence is this one. Box it. Put a box around it. And the independence check is this guy. Note, do not assume 2 events are independent unless you are told they are independent or you can reasonably assume they are, like coin flips. Obviously, if I flip a coin and it comes up heads, that has no bearing on what the next coin flip is going to be. But for the most part, you shouldn't ever assume independence between 2 events. Don't ever do it because it's going to get you in trouble. Don't use this rule unless you're told they're independent. So let's have a look. Suppose that 70% of people like Doritos and 40% of people like Mountain Dew. Delicious, fantastic combination of snacks. I'm sure that some of you guys are like, yeah, I too am a gamer. 30% like both. Are liking Doritos and Mountain Dew independent? Now I know your brain instantly wants to go to a Venn diagram, and you could do a Venn diagram for this. You could go ahead up and set up some circles and all that, put Mountain Dew and Doritos. But for now, I don't think I'm going to do that just yet. I might do that, say that for the next part. I'm just being asked, are they independent? So independence is probability of Mountain Dew times probability of Doritos would need to equal probability of Mountain Dew and Doritos. Well, we are told all three of these values. Probability of Mountain Dew is 0.4. So I'm going to put 0.4 right here. Doritos, that's 70%. So that's a 0.7. That's going to go here. I'm going to multiply these. This gives me 0.28. But how about on the right-hand side? What's the probability that people like both? 30%. Do these match? No match. So I'll even put a does not equal sign there. Does not equal. No match. So they are not independent. All right. Next question. Suppose that 70% of people like Doritos and 40% of people like Mountain Dew, and then it says these events are independent. Okay, so now we are told they're independent. Well, guess what that means? If I know the probability of Mountain Dew is 0.7, and I know the probability of Doritos is 0.4, well, then I can multiply them to get the probability of Mountain Dew and Doritos. So I know this will end up being 0.28. I'm allowed to multiply these two probabilities now. And now that I have my overlap value, I'm going to go and make my Venn diagram. Let's draw my circles. Let's fill this in blue. Big circle here. Big circle here. Let's put M for Mountain Dew and D for Doritos. I'm told, no, again, a lot of people are very tempted to put a 0.7 here, or sorry, a 0.4. 70% for Doritos, 40% for Mountain Dew. I kind of flipped it around. That's okay. You guys can keep up with me. Mountain Dew is 40%, but you can't put 40% here. And in the same fashion, 70% are Doritos, but you can't put 70% here. You have to wait to figure out what's in the middle. And as we just established by the independence rule, 28% is in the middle. So put a 0.28 here. And now that I have that, I can figure out how much goes in the Mountain Dew circle and the Doritos circle. Mountain Dew, 40%. Well, I just established that 28% is here. If I take 28% away from 40%, I'm left with 12%. And if 70% is here, 70% minus this 28% is 42%. So now I've got to get my last value. Let's see, 28 and 42 is 70, plus 12 is 82. Subtracting 82 from 100% gives me 18%. And now I can answer some questions. Make sure you're doing your Venn diagram just like me. If the events are independent, what's the probability that someone likes Doritos, but not Mountain Dew? So likes Doritos, not Mountain Dew. So which part of my Venn diagram is that? So they're inside the Doritos bubble, but outside the Mountain Dew bubble. That's this guy right here. Likes Doritos, but doesn't like Mountain Dew. So 0.42. Okay. Next question. Bennett and August's preferences for Doritos and Mountain Dew are independent. All right, there's that word again, independent. What's the probability that exactly one of them likes Mountain Dew? So what that means is if exactly one of them likes Mountain Dew, it could be that Bennett likes Mountain Dew. Bennett likes it, but then August doesn't. Or it could be the case that Bennett doesn't like it, but August does. Okay, so I got to figure out those probabilities. Well, what's the probability that any one person likes Mountain Dew? Let's go all the way back to the beginning. It says that 40% of people like Mountain Dew. So the probability that Bennett likes Mountain Dew is 0.4. And if there's a 40% chance that you do like Mountain Dew, there's a 60% chance that you don't. So Bennett likes it is 0.4, but August not liking it is 0.6. On the other hand, Bennett could be the one who doesn't like Mountain Dew, in which case there's a 60% chance that he doesn't. But if Bennett doesn't, then August must in order to satisfy the conditions set forth for this problem. And the probability that August does is 0.4. So I get 0.4 times 0.6, that's 0.24. 0.6 times 0.4 is 0.24 again. These are being added for an answer of 0.48. Why am I adding them? Because I'm talking about the two different possible cases. It could be the case that Bennett likes Mountain Dew and August doesn't. Or, and what have I told you that the word or means? Or means add. So it could be the case that Bennett doesn't and August does. So I multiplied those to get that probability. Adding those together gives me 0.48. All right, going to move on to conditional probability. Talk about how to compute that. It's possible that the probability of an event changes when some other event happens. For instance, it says that 90% of people have a driver's license. What percent of 18-year-olds have driver's license? So some of you might think, okay, well, maybe you knew some people who, when they were 18, hadn't yet gotten their license, but I would probably say less. What percent? I don't know. I don't know the number. I'm just gonna make a number up. Let's say it's 80%. I know you probably can't see it because my big dumb head's in the way. No, just barely. Let's make me turn into a ghost. There I am, a ghost. Ooh, scary. So yeah, you might, if I said 90% of all Americans, that includes most adults, like all the old folks. But if I'm talking about 18-year-olds, well, you might have some friends who took their sweet ass time getting their license. Some of you out there probably still don't have your license. That's not no judgment, but it's less likely for some of those younger folks to have their license. So that probability has changed from 90% down to 80%. Let's do another extreme example. 95% of people know how to dribble a basketball. What percent of NBA players do you think know how to dribble a basketball? If I went up to an NBA player, what's the probability? What are the chances that the NBA player knows how to dribble a basketball? It's 100%. Every basketball in the NBA basketball player in the NBA knows how to dribble a basketball. So it's changed where 95% of people know how to dribble a basketball. Maybe there's some 5% who are just really bad at it. They just have no rhythm whatsoever. But the moment you ask an NBA player, that probability shoots up from 95 to 100%. So that's what conditional probability is doing. The probability changes when you know some information about the observation. So that's what we're going to be doing when we see these problems. So we're going to use this formula, little box around it. This is the probability formula for conditional probability. This is read as A given. That little vertical bar means given, okay? Probability of A given B. Let's do another Mountain Dew and Doritos example. I'm going to draw the same Venn diagram. Actually, you know what? We're not drawing a Venn diagram. Screw it. We don't need it. I want to know, what's the probability that a student likes Doritos given they like Mountain Dew? Given they like Mountain Dew. All right, well, let's just use the conditional probability formula. You need to memorize this. If you haven't memorized it yet, memorize it now. Pause the video. Let it sink into your brain. You need to know this formula. You must. So A given B is A intersect B divided by probability of B. So that means probability of D given M is P of D and M divided by probability of M. Well, guess what? These probabilities were literally given in the problem. 40% of people like Mountain Dew. That's my denominator. That's my P of M. So 0.4 goes down here. 30% like both. That's my numerator. This is D and M. This is just M. 40% of people like Mountain Dew. That's P of M. 30% like both. That's D and M. So put a 0.3 in my numerator. 0.3 over 0.4 is 0.75, which gives us our answer. Okay, let's do another conditional probability. What I want to do for this question is kind of disguise the language. I was very nice to you in the first question because I literally said the word given in the problem, given they like Mountain Dew. But I'm not going to be always that. I'm not always going to be that nice. This says, what percent of Dorito lovers also like Mountain Dew? The fact that I said percent of Dorito lovers, this is telling you given D. Given that they like Doritos. Now I've disguised it. I didn't say the word given anywhere in this problem, right? I didn't say given. It's kind of tricky. But I'm not asking about what percent of all people. I'm asking just out of the Dorito lovers. So I want to know the probability somebody likes Mountain Dew given they like Doritos. So I'm going to invoke the formula again. P of Mountain Dew and Doritos divided by probability of Doritos. That's the conditional probability formula. Again, I'm going to consult my values at the top. 70% like Doritos, 30% like both. So that means I'm going to put 0.3 on the top and 0.7 in the bottom. This would be my answer. I guess that would simplify to 3/7 if you want to do that. There's your answer. Okay. This next question is really hard. I'm going to put a star next to it. It is so hard that I don't even think your professor is going to ask it, but if you can handle this type of question, then you can handle any sort of conditional probability question. The train to Dallas is on time in 60% of the time. So let's say probability of T for on time, 0.6. When it's raining, so this is your given, when it's raining, given. When it's raining, the train to Dallas is on time only 50% of the time. So we're going to say probability of it being on time given that it's raining. That's 0.5. Suppose there's a 20% chance of rain every day. So probability of rain equals 0.2. Now the question wants to know, what's the probability that it's raining on a day where the train is on time? So they've already told you this is another given. Train is on time. That is given. So they want to know probability of something given train is on time. Well, guess what? We want to know what's the probability that it's raining. This is a really, 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 really hard question. I'm almost tempted to skip it because, again, I don't think you're going to see something as difficult, but if you do, you'll at least be prepared. So they've given you all these things. They've given you these three values over here on the left, and our goal is to find this guy, probability of rain given train is on time. Let's use probability of rain and time divided by probability of time. So looking at this, do I have these values? Well, I don't have rain and time, so we'll skip that. But I do have probability train is on time. I have that as 0.6. So I have my denominator. So now you think, okay, well, it seems like we're screwed. We don't have that other value. But take note, what haven't we used yet? We've just used this guy. So let's cross him off. We don't need him anymore. We just used him. But we have these two remaining values here. P of t given r and P of r. Well, what's the formula for P of t given r? It's like another conditional probability. P of t given r equals P of t intersect r divided by P of r. And I have two of the three values here. I have P of t given r. I have that this is 0.5. I have that the value down here in my denominator is 0.2. So P of t intersect r, the unknown value, can be solved for. I can solve for it. Let's scoot this up a little bit. And I find that P of t given r, if I just multiply both sides, or t and r I should say, is 0.5 times 0.2 ends up being 0.1. So I have this value, and guess what? That's the missing value I need. I can take this guy, put it up into my numerator right there. Now you might look at me and say, well, Andy, hold on a second. Why can you do that? This says rain and train is on time, but this says train on time and raining. Well, guess what? Rain and train on time is the same as train on time and rain. So I can swap these, and the and is still true. So the 0.1 goes in the top. I get a final answer of 0.1 over 0.6, which is 1/6. Again, I think that's super hard. If you want to rewind the video and rewatch that one, you can. But again, put a star next to this because this is probably harder than something they would ask in an exam. They don't think they would ever throw some crazy conditional probability like that at you. Okay. We are going to go to probability with a table. Tables are pretty easy. Just read the table for the values in it. That's kind of it. Suppose that a score a student gets on the first ECO329 exam has probability distribution summarized in the table below for the 300 students taking ECO329. What is the probability that a student scores 80 or worse? Well, 80 or worse means this number or that way. So 80 or worse, what are the associated probabilities? 0.1, 0.2, and 0.4. That's it. Simply add those values up and you're done. Super easy, right? Just add the values and you get 0.7. That's it. 70% chance somebody scores an 80 or worse. That sounds kind of disheartening. How many students score at least an 85? Your professor loves doing this. How many students score at least an 85? As a reminder, you were told 300 students were taking ECO329. And I want to know what's the probability, or no, not probability, but how many of them scored at least a 85. Well, at least an 85 means they scored a 90, right? If you scored 60, you didn't score at least an 85. You scored a 70, you didn't score at least an 85. You scored an 80, you didn't score at least an 85. If you scored a 90, you did. And there's what percent of the students do. So it says that 30% score at least an 85. There's 300 students. So 300 times 30% gives me 90 students. There are 90 students who got 85 or better. Okay. Again, your professor loves doing questions like that where these are probabilities and he asks for numbers, or vice versa. There are plenty of questions where, and you'll see this on my mock exam, I think that's on my mock exam, a question where I give you these numbers, I say like, I have 0 siblings, 1 sibling, 2 sibling, 3 siblings, but then I tell you how many people have that. So like maybe 50 people are only children, and maybe 70 people have a brother or a sister, or 80 people have a brother and a sister, or 2 brothers or 2 sisters. And then maybe you have a family, you've got 3 siblings, and oh god, what a crazy household that would probably be to live in. But you get the picture. Here I'm giving you numbers of people that said this result, and then you need to divide this by the total number of respondents to figure out how to get these terms of probability. So just bear in mind, your professors will want you to move fluidly between numbers of students and percentages based on a table like this. Let's do a 2-row, or sorry, not 2-row, but column and row table. It's a little bit harder because the table's bigger, and so people get a little lost. Let's see if we can do this. What is the probability that Andy sees Arcade Fire on weekend 1? So Arcade Fire, here it is. The Arcade Fire is here, but this is Arcade Fire on weekend 2, so do not count this. I don't care about this. I want weekend 1 Arcade Fire. So that's all of these values here. 0.05, 0.09, 0.07, and 0.04. That would be 25.25 is the probability there. Okay, next one. What's the probability that Andy sees gorillas but not the strokes? There's two ways to do this. Gorillas but not the strokes. It could be the case. Let's see. I want to see gorillas, so this would be gorillas, this would be gorillas, this would be gorillas, but notice it's the strokes, so I can't count it. So gorillas, gorillas, I can't count this 0.15. It is gorillas, but I said I can't see the strokes, so I'm not going to count this one. And gorillas, so gorillas, 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 but not the strokes. And then I can also say gorillas, gorillas. So everything I have a check next to, oh, sorry, no. Whoa, that's an X, that's the strokes. I can't count that either. So the only things I have a check next to, remember, it's gorillas, but not the strokes. So looking at this table, I've got 0.12, 0.03, 0.09, and 0.01. This adds up to be 0.25 again. Kind of odd that happened. I did not intend for that to happen, but I think I got 0.25 again. 12 and 15, or 12 and 3 is 15, plus 10 is 25. Yeah, how about it? 25% again. All right, we're gonna do more probability from the table because I guess these kind of mess people up just because, I don't know, they're misreading the table. It's really important to read the table correctly. What's the probability Andy sees Arcade Fire and the strokes? Oh, my green screen's falling apart. Yes, I'm not really in a padded cell. I'm in a room, my studio office. There we go. But no, padded cell, back to the padded cell. What's the probability Andy sees Arcade Fire and the strokes? And the strokes. So I need Arcade Fire and the strokes. This will work. Arcade Fire and the strokes. So will this. This will also work. 0.07 is Arcade Fire weekend 1, but the strokes on weekend 2. So notice there's two ways to get this done. I can see Arcade Fire on weekend 1 and the strokes on weekend 2, or I can see the strokes on weekend 1 and Arcade Fire on weekend 2. Adding those together, 0.07 plus 0.14 gives me 0.21. Okay, what is the probability Andy sees Arcade Fire or the strokes? Now that's going to be a lot more values. So Arcade Fire or the strokes. This is Arcade Fire, this is Arcade Fire, this is Arcade Fire, this is Arcade Fire. This entire column is Arcade Fire, so that counts. This is the strokes, this is the strokes, this is the strokes. All this column is the strokes. Okay, now let's go to the rows. Arcade Fire, got all these, and then lastly the strokes. So all 10 of these values get checked, which basically means every single value except these last two. I'm probably going to just do the following. If this value is 3% and this value is 1%, that means a 4% chance I don't see Gorilla or Arcade Fire or the strokes, which means there's a 96% chance that I see Arcade Fire or the strokes. That's your answer to that question. All right, what's the probability that Andy sees the same band on both weekends? I wish I hadn't drawn all these check marks because now it's going to get confusing. Same band both weekends. So that would be Arcade Fire twice, Gorillas twice, and the strokes twice. So adding up those probabilities, 0.05, 0.03, 0.02 is 0.10. Okay. Hopefully we're not beating a dead horse here, because again, I know that we're doing a lot of probability table. There's one more question I want to get to, at least one more I want to get to, where I'm doing a conditional probability. So this says, what's the probability that Andy sees Twin Shadow, given that he saw gorillas on weekend 1? So we're going to say probability of Twin Shadow, given gorillas, and make sure that we say gorillas on weekend 1. Okay, so let's go to our conditional probability formula. I wish I hadn't made this so darn large. Probability of Twin Shadow, not Taylor Swift. I know some people say TS. Oh, that's Taylor Swift. No, that's Twin Shadow and gorillas on weekend 1 divided by probability of gorillas weekend 1. All right, let's start with my denominator. Gorillas weekend 1. Gorillas weekend 1. Gorillas weekend 1. That's these values. 0.12, 0.03, 0.15, and 0.01 is 31%. So that's my denominator, 31%. My numerator is probability of, I almost said Taylor Swift. Not Taylor Swift. TS is Twin Shadow. Twin Shadow and Gorillas Weekend 1. So Twin Shadow and Gorillas Weekend 1. That's this value. This is the only value that is both Twin Shadows and Gorillas on Weekend 1. So that's my numerator, 0.01. And so my answer is this guy here. Tough question, tough question. Last one on this page says, are Andy's choices independent? The way you're going to do this is, I'll tell you what the steps are. You pick a cell. So go to the table, pick any cell you want. Pick a cell. Okay, I'm going to pick, let's do this cell right here. So pay attention. I'm going to pick this cell, this 0.2 right here. What you're going to do is you're going to find the column sum and the row sum for that cell. What I mean by that is, look at the column the cell is in. It's strokes. So probability of strokes, at least strokes on Weekend 1, I'll say Weekend 1, is what? 14 plus 20 plus 2 plus 8. That would be 44.44. Okay, so 0.44 there. I also want you to get the row sum. So we just added up all the values in the column that contains that cell value that I picked. Now I want you to do it for the row. So now add up all the row values. 0.09, 0.03, 0.20. This would be probability of Gorillas Weekend 2. And this would be 9 plus 3 is 12 plus 20 is 0.32. And now the question is this. If I multiply these two values, do I get the cell value? So if I take these two values and multiply, do I get the cell value? Grab a calculator. Moment of truth. 0.32 times 0.44. Will this match the 0.20? No, it does not. I get 0.14. So if I took probability of strokes on Weekend 1 times probability of Gorillas, I get 0.1408. Let's just say 14. Yeah, let's just say 0.14. These don't match. This value doesn't match this value. No match. No match. And so because they don't match, my choices are not independent. Not independent. Good. I'm using that independence check to determine whether or not these events are independent. Okay. How are we doing on time? I have no idea. There's no time in here in this padded cell. Let's do advanced counting, committee form. We're gonna get to committee forming and then take a break. I love it. Okay, we got 4 more pages. We'll take a break after that. Let's keep it going. Under certain circumstances, it won't be possible to calculate a conditional probability the way we like to. We actually get these layers of properties that describe either some people or states or observations or dog breeds or whatever, and we have to break that down using a tree diagram. So this formula is gross. You can use this, by all means, use this formula if you want to. If you feel like you understand this formula, great, you are a psycho. But I don't like this formula, and many of you don't like this formula either. Tree diagram is going to make your life super easy. So this formula is gross. Let's talk about a better way to put this idea to use, the tree diagram. So let's look at this problem. Experts predict that the probability of Texas beating OU is 0.8. The probability of Texas losing to OU is 0.2. And then there's this next layer. The first layer is, does Texas win or not win? Now there's this next layer, based on what happens when Texas wins or if they don't win, heaven forbid. Furthermore, you'll party too hard and wake up sick with probabilities 0.7 if Texas beats OU and 0.4 if Texas loses. What's the probability to wake up sick? This is a classic Bayes rule question. We've got a first layer, which again tells you the probability that Texas wins, but then based on that, what happens by some sort of probability of partying afterwards. So the steps you want to do are as follows. I want you to write these steps down. Step 1, label nodes with events. Step 2, label edges with probabilities. Step 3, which I know you can't see just yet. Step 3, multiply down the tree. Write these steps down. I need you to memorize them because this is going to make your life easy. Okay, we're going to draw a tree. Branch, branch. Okay, UT either wins or loses. Okay, based on whether UT wins or loses, there's a chance you're going to be sick because you partied too hard. So S and NS for sick and not sick. Okay. Now we've set up our tree. Every node has been labeled with an event. Now you might say, well, what about this guy? We never labeled the first node. Don't worry about it. We're not going to. Label the edges with probabilities. Well, we were told that the probability that Texas beats OU is 0.8 and loses is 0.2. Okay. Now, if Texas wins, that is to say, if you go down this branch, how likely are you to wake up sick? Well, it says that you'll wake up sick with probability 0.7 if Texas wins, if Texas beats OU. So 0.7 here, and therefore, if there's a 70% chance you wake up sick after Texas beats OU, well, guess what? There's a 30% chance that you don't wake up sick. Okay, keep it going. If Texas loses, then the probability you wake up sick is 0.4, and therefore the probability you don't wake up sick is 0.6. Every edge has now been labeled with a probability. So step 1 is done, step 2 is done, and now we are proceeding with step 3, which is to multiply down the tree. Here we go. 0.8 times 0.7 is 0.56. 0.8 times 0.3 is 0.24. 0.2 times 0.4 is 0.08. And 0.2 times 0.6 is 0.12. We're going to look at these values and these values only. You're only ever going to play with the values in this box. Put a box around it. We've multiplied down the tree. Put a box around it. We're only going to touch those values. The first question says, what's the probability that you'll wake up sick? It might be one value. It might be multiple values. And in this table, I see that sick corresponds to a 0.56 as well as a 0.08. So these two values get added together. Find the probability of you being sick. Probability of sick equals 0.56 plus the 0.08, which gives me 0.64. That's your answer to this first question. That's it. Probability you wake up sick. Next question. What's the probability that Texas wins and you wake up sick? Now, I don't want you to think I need to multiply because I said the word and. I just want you to go back and look at the table of values that we had. And I want Texas wins and you woke up sick. Well, of these four values, the only one where you woke up sick and Texas won is the 0.56 here. So we're going to put that as our answer to this next question. So Texas wins and you woke up sick. Notice how I'm only just using the tree diagram. You're going to think, oh my God, I'm not even using this disgusting formula. Yeah, screw this guy. This guy sucks. Tree diagram is the way to go. All right. Last question. Given that you woke up sick, they're always going to say some sort of given for these Bayes rule questions. You have to figure out what that given is. Given that you woke up sick, so if you want to say probability of something given sick, what's the probability that Texas won? So W goes here. One given sick. Okay? We're going to say equals probability of when intersect sick divided by probability of sick. Now, some of you might be astute. The astute observers among you might say, hey, wait a second. Didn't we already find probability of sick? Yeah. Sometimes your professor will lead you down a garden path. He'll say, hey, I want you to find the probability of sick. And guess what? Now that I found it, might as well just use it. I mean, let's just say you forgot. And more likely than not, you guys are you're in your own world when you're taking these exams. You're going to forget that you actually found this value. So tell you what, go back to the table. Which of these values correspond to me being sick? It's this first guy, sick, and the third guy, sick. So add those two probabilities, 0.56 and 0.08. That gives me my denominator of 0.64. But again, that's the same value that we found right there. The numerator is win and sick. Guess what? We found that value too. That was this guy. Probability that Texas wins and you wake up sick. But again, if you want to consult the table, win and sick is this 0.56 here. That's going to be my numerator. So 0.56 goes here. You can leave your answer as that, or you can write your answer as 0.875 for your final answer. That is a Bayes rule question. You probably want to see it done again. Let's do it again. Andy is dealing with a faulty alarm clock. Beep, beep, beep. I hate those things. On 70% of days, the alarm works just fine. On 20% of days, I snooze the alarm. And on 10% of the days, the alarm just doesn't work. Just fails to go off. So those are the three cases. I'm going to set up my tree right away. Let's say W for works, S for snooze, and F for fail to go off. So it either works, I snooze it, or the alarm fails. So those are my three cases. And then based on that situation, I will either wake up as planned 90% of the time. Let's see, wake up as planned. I shouldn't use W for that. Let's see, what's a good letter to use for woke up as planned? Let's say I for intended. I don't want to use P because P is what we usually use for probability. Let's say I for woke up as intended, and then didn't wake up as intended. Woke up as intended, didn't wake up as intended. Woke up as intended, didn't wake up as intended. So there's my tree. Every node is labeled. Now it's time to go with some probabilities. Label our edges. 70% of the time, it works. 20% of the time, I snooze it. 10% of the time, it doesn't work. Now, if the alarm works properly, I wake up as planned 90% of the time, and therefore I don't wake up as planned 10% of the time. What if I snooze it? If I snooze it, oh, you know what? It says forgets to set this is a typo. It says forgets to set his alarm. This is a stupid typo. This should have said when he snoozes it, when he snoozes. So erase where it says when he forgets to set and change it to say, my dumb head's in the way. When he snoozes his alarm, he wakes up 50% of the time. So 0.5 here and 0.5 here. Okay? And lastly, when his alarm clock goes off, he wakes up as planned, or sorry, when the alarm clock fails to go off, make sure you're reading properly like I just didn't do, fails to go off, he wakes up 30% of the time. So 30 and therefore 70. Okay? Every node is labeled, every edge is labeled as well. We're going to multiply down the tree. 0.7 times 0.9, 0.63. 0.7 times 0.1, 0.07. 0.2 times 0.5 is 0.1. 0.2 times 0.5 is also 0.1. This is 0.03. And this is 0.07. So we have our table of values. And let's start with the first question, which says, what's the probability that Andy wakes up as planned? That's the I value. So I wake up as planned here, here, and here. 63, 10, and 3. That makes for 76%. That's my answer. That's it. Tree diagram is chef's kiss. It's wonderful. It makes everything so easy. What's the probability that Andy forgets to set his alarm, or this needs to change. This should say snoozes. Snoozes. What's the probability that Andy snoozes or he wakes up as planned? So snoozes are these two values. Snoozes and snoozes. And then there's two others. There's intended. So again, it's an or situation. Either I snoozed it or I woke up as intended. Anything that doesn't satisfy at least one of those is out. So 63, 10, 10, and 3 makes for 86.86. Again, snoozes or wakes up as planned. That's all the I's and everything that falls in the snooze category. All right, last question. If he wakes up as planned, this is a given. This is the given. What's the probability the alarm failed to go off? So what's the probability the alarm failed to go off given I woke up as planned, given I woke up as intended? I cite my conditional probability formula. So F intersect I over probability of I. Let's go hunting for these values. Probability of I found that one already. Woke up as intended was 0.76. But if you don't believe me, just add the 0.63, that's an I. 0.10, that's an I. And the 0.03, that's also an I. So that gives me 0.76 in my denominator. How about my numerator? Probability that alarm failed to go off and I woke up as intended. Well, that's merely this value. This is the only value where alarm failed to go off and it worked and I woke up as intended. So 0.03 is my numerator. That's the only value for we have F and I. 0.03. This is my answer. That's it. Bayes' rule is super easy with the tree diagram. So make sure you're doing that when you try my practice problems as well as the one your professors have given you. Okay. We've got some advanced counting rules. These are a little bit harder. We've got factorial, choose, and permute. Now, the one you're going to see most often is this guy. You want to be really familiar with choose because most of the problems you encounter are going to be using choose. But let's see. Hollywood is planning on making 12 blockbuster movies, one for each month of the year for 2025. Writers have submitted 18 scripts. How many different combinations of movies can be chosen? It's stupid. Green screen. Okay. How many different combinations of movies can be chosen? Well, I have 18 scripts. I can choose 12. Now, how does that get written? You might see it written like this, 18 choose 12. Or you might see it written like this, 18 choose 12. Both of these are acceptable. Okay. Your answer, it's very tempting to want to write a fraction bar. I know that a lot of people just do put a little fraction bar out of habit, habit, not habitat, out of habit, just because we think one number over another, that's a fraction. Choose doesn't work like that, no fraction. But you might be curious what this number is. TI-84s can calculate it. Let's do this. Math over to prob. There's my NCR function. 18, choose 12. This value is 18,564. Now, do I expect you to be able to do that on the exam? No, because your professor expects you to say, you know what, you can leave your answer like this if you want to. Just leave it as 18, choose 12. That's totally fine. Okay, among the 18 scripts, 8 movies are dramas, 6 are comedies, and 4 are action movies. How many ways are there to select 5 dramas, 4 comedies, and 3 action movies? So we want that there are 8 movies that are dramas. 8 movies are dramas. And I want to select 5 of them. So 8 dramas, select 5. 8, choose 5. And now, and I need to choose my comedies. There are 6 comedies. And I want to choose 4 of them. So 6, choose 4. And then lastly, 3 action movies. Well, there are 4 action movies to pick from. And I want to choose 3. This is my answer to this question. Simply that. All multiplied. I have 8 dramas. I want to choose 5 of them. I have 6 comedies. I want to choose 4 of them. And I have 4 action movies. I want to choose 3 of them. That's it. That's all you have to do for that question. This one is tricky. Put a star next to it. How many ways are there to select none of the action movies? No action movies. So it's going to be helpful to say, well, we've got 18 movies. Yes, a moment ago we said 8 of them were drama and 6 of them were comedy and 4 of them were action. But now we're going to do this. We're going to say there are 4 action and 14 non-action. It's going to be more helpful for us to figure these out in terms of action versus non-action. That's it. But how many ways are there to select none of the action movies? There are, remember, don't forget, this whole problem, we're choosing 12 movies. I think a lot of people forget that. A lot of people forget that what was Hollywood planning on doing? They're planning on making 12 blockbuster movies, 1 for each month of the year. So you got to remind yourself, going way back to the beginning of the problem, we're always choosing 12 here. Okay? How do you choose 0 action movies? Well, there are 4 action movies. Like I said, you're choosing. I'm such an idiot. I put it down here. Back up here. There's 4 action movies, but I'm selecting none of them. None of the action movies. So 4, choose 0. Well, what about the rest, right? Because if you've chosen 0 action movies, that means the other movies, you must have chosen 12 movies from somewhere else. And yeah, you chose them from the 14 non-action movies. So there's a 14, choose 12 here. So there are 4 action movies. I chose 0. Because again, it says none of the action movies are being chosen. Well, how many movies are left? There are 14 other movies. Some of them are drama, some of them are comedy. We don't really care which ones are which. We just know that they are not action movies. That's all we care about. And we have to choose 12 of them. So 14, choose 12. So this is your answer to this question. All right. Now we're going to do some factorial. This is where the next 2 are going to be reordering. So reordering is starting to make me think, oh, I need a factorial. Okay. So once the 12 movies are chosen, how many different reorderings of the movies are there over the course of the year? So you have 12 movies. I could do movie 1, movie 2, movie 3, or I could switch up the order. I can mix them all up, right? How many different ways are there to rearrange them? 12 factorial. That's your answer. Now it looks like someone just excitedly saying the number 12. 12! 12! No, it just means 12 factorial. And that's the number of ways to rearrange them. If you want to see what that looks like on a calculator, again, you're not expected to do this, but I'm sure some of you are just dying to know what is 12 factorial. 12 math over to factorial. There it is. Big old exclamation mark. So that's big number here. 400 and, is that a billion? No. 479 million, 1,600. Wow, big number. Okay. Don't write that number down. Just leave it as 12 factorial. And again, not everyone's going to be using a calculator like this one on the exam. So you just leave it at 12 factorial. Okay. Suppose that 4 of the 12 movies chosen are drama films. How many reorderings of the movies are there if the dramas must appear in the last 4 months of the year? So what we're saying is we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We've got 12 months. And the last 4 have to be drama. So drama, 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 drama. So what that means is these other movies can be rearranged. So we have 8 movies here. We have 8 here and 4 here. Okay. Well, guess what? These 8 can be rearranged among themselves. So this will be an 8 factorial. And the dramas here at the end can also be rearranged among themselves. So this is your answer here is 8 factorial times 4 factorial. And that's it. I don't know how this might start to cross into the threshold of too difficult for your professor to want to ask. So I'll put a star next to this as well. But I don't want you to be prepared for anything that gets thrown at you, right? So the first one was pretty easy. There's 12 movies. How many ways can you rearrange 12 movies? 12 factorial. Easy enough. But what if the last 4 have to be dramas? Well, now I can rearrange these movies however I want, and the dramas can be rearranged in these last 4 months of the year. But that's it. So 8 factorial times 4 factorial. That's your answer here. We've got one last section before I take a break. I probably should have taken a break sooner. I know you guys are probably burnt out this first part, but that means the second half will be super short. All right, committee forming. This is more choose. So anytime you see committee forming, it's gonna be like, 9 choose 3 or 7 choose 4, a bunch of stuff like that. Okay, let's start this problem. We got a committee of really lame people are to be made from a group of 6 A&M students, 6 Texas A&M students, and let's move my big dumb head, and 7 OU students. How many different 5-person committees can be formed consisting of 3 A&M students and 2 OU students? So remember, we have 6 A&M, sometimes it just helps to write this, and 7 OU. And we want to make a 5-person committee of really lame people. Okay? All right, let's kick it off. We've got 6 A&M students, but I want to choose 3. The committee's got to have 3 A&M students on it. So 6 choose 3. There are 6 A&M students. We're choosing 3 to make it a really lame committee. Furthermore, we have 7 OU students, but we only want to choose 2 of them. So 7 choose 2. That's it. Your committee has been formed. Done. We did it. That's it. Let's do another. Again, we want to form a 5-person committee consisting of 3 A&M students and 2 OU students. Goofus and Bubba are both Texas A&M students. How many different committees can be formed where Goofus or Bubba or both are on the committee? So let's say we had 6 A&M and 7 OU, but among the A&M students, we have 1 Goofus, 1 Bubba, and 4 others. So we'll say others. Okay. Now this tree diagram is making you think Bayes rule, I know, but we're not doing this for probability or for like a probability tree. We're just helping us trying to figure out and kind of compartmentalize all the different possible cases. So we want to know how many different committees can be formed where Goofus or Bubba or both are on the committee. So watch carefully. I'm going to say Goofus is on the committee, so there's only 1 Goofus and I'm choosing him. I'm not choosing Bubba, so yes Goofus, no Bubba. And don't forget, I'm supposed to choose 3 A&M students. I've already chosen Goofus, so I need to choose 2 more A&M students, right? Goofus was an A&M student. I need 3 A&M students, so I need 2 more. And I have to choose that from the 4 other A&M students. There's 4 other A&M students from which I'm going to choose 2. And then I have to go and choose my OU students, of which there are 7, and I'm choosing 2 of them. Now, that is yes Goofus and no Bubba. But it could have been, so plus, yes Goofus and no Bubba, or no Goofus and yes Bubba. Oops, yes Bubba. I choose my 2 remaining A&M students, and I choose my 2 OU students. So, no Goofus. Yes, Bubba. Okay. And lastly, don't forget, it says Goofus or Bubba or both. So we've got one last one to add. Plus, Goofus, yes. Bubba, yes. Now, if Goofus and Bubba are both on, it's actually kind of funny having to say Goofus and Bubba over and over. Yes, Goofus and Bubba. That means they're only choosing 1 more A&M student from the 4 remaining. I've got now 3 A&M students, and I choose my 7 choose 2 OU students. Here we go. Last one. We've got how many different 5-person committees can be formed with majority OU students. Now we're not restricted to say, it used to be the case we had to have 3 A&M and 2 OU. We're not doing that anymore. This is gone. Now we're doing majority OU. Well, how can that happen? You could have in a 5-person committee, it's got 1, 2, 3, 4, 5. You could have 3 OU, you could have 4 OU, or you could have 5 OU. That would be majority, right? In a majority where there's 5 seats, majority would be 3, 4, or 5. So how's that possible? Well, we get 7 OU students choosing 3. Say 3 OU students. And then we say times 6 choose 2, so we get 2 A&M. Or, so we'll put plus, or we get 4 OU students, but then that means we only have 1 A&M student. Or we have only OU students and 0, move this out of the way, or in the 0 OU students, A&M students, 0 A&M students. That's an A&M, believe it or not. This would be your answer to how many different committees can be formed where a majority of them are OU students. Okay, it is now time to take a break. We've been at it for, I'm sure, what it feels like at least an hour. Take a breather, get some water, use the restroom, let your brain rest and relax. I'm going to hit the stop recording button, and we'll be back for part 2 in just a second. Of course, I want to remind you, if you have any questions about anything you've seen, hit me up. That's what I'm here for. Andy at gpafactory.com. I'll see you guys in the next video.